first we're going to talk about the types of circuits that exist. And first there is a series circuit, which is the basic circuit. And a series circuit is a portion of a circuit that provides a single conducting path without any junctions. And what we'll see here is that the path of the charge carriers would flow through each element in the series circuit and come back to the other terminal. Whereas in a parallel circuit, there are two or more components in a circuit that are connected across common points or junctions, and these provide separate conducting paths. So for example, what we'll have is part of the charge will go through here and come back through, while at the same time another part of the charge branches off and goes here and through the second bulb. Another part of the charge branches off here and goes to the third bulb. So these all occur on different conducting paths. Start with a series setup here. And we're going to take a look at three things in series. We're going to look at the current, the voltage, and the resistance to understand our laws. And the first thing to notice is that the current through or across each resistor is the same. It's like the flow rate of water through a pipe. If you had a pipe set up and you had sensors here, here, and here, and those sensors were able to sense the current of the water here, and then here, and then here, there'd be no change in the current. They'd be occurring along the same path because the water is still flowing through the same location. So what we say is that the current in a series circuit, again, is equivalent across each of these resistors. So we'll say I1, I2 equals IN. IN meaning as many resistors as there are. So if there were 10 resistors, we'd list I equals I1 equals I2 equals I3 equals I4, etc. And this is important to know when we do some calculations in a minute, that the current across each resistor in series is the same. Now for the voltage, we can think about the fact that the potential difference across the battery is really equal to the potential difference across the total load, or the sum of the load across each resistor. And what that means is that the voltage is equal to the sum of the voltages, or the voltage drops, across each resistor. So if there's 5 or 6 resistors, each of them take on a certain amount of voltage or potential difference, and as a result, the sum of all of them is equal to the potential difference provided by the battery or the source of energy. Now the third part that's a little bit more confusing though, and we're going to derive this third part, is resistance. And if we remember that V equals IR, Ohm's law, applies to each resistor, so for two resistors what we can say is that V equals V1 plus V2, and that comes from here. Imagine we just had two resistors. Right? We could replace each of these V's with IR. So the current across the entire circuit times the resistance of the entire circuit, and I'll explain what EQ means, is equal to the current across the first resistor times the resistance across the first resistor, plus the current across the second resistor times the resistance across the second resistor. And now what we have to do is take a look back at our current law. Our current law said that the current were the same throughout each of these resistors. So this I, and this I, and this I, these are all the same. Well, if all those I's are the same, what I can do is just write them all as simply I. So what happens is this becomes without any subscripts, right? And now I could simply cancel all the I's. And it's not obvious maybe, so maybe just factor it out so you can see. But really just factoring out an I. And then the I's cancel on both sides. Leaving behind our law of resistance in series, which states that the equivalent resistance of a circuit is equal to the sum of the resistors in that circuit. So what this means really is that if we had 5 resistors, we could really, and this is mathematically speaking, replace those 5 resistors with one resistor that is equal to the sum of all the resistances across those 5 resistors. So if we write this law out, that was just for the example of 2 resistors, it would say the following. The equivalent resistance in series is equal to, again, the sum of all of the resistors. So example 1 says a 9-volt battery is connected to 4 light bulbs as shown in the figure to the right. Draw a schematic representing this and then find the equivalent resistance for the circuit, that REQ value. From this then determine the current in the circuit and also find the voltage drop across each resistor. Now, we can see that the voltage, or the charge carriers, are leaving the terminal and going through each resistor in series here. So if I were to draw a diagram, I would start with some sort of a voltage source. Now I have the terminal, the positive terminal, and we remember that we're looking at the positive flow of charge with current, so I'll leave that. It will then enter the 7 ohm resistor. And it doesn't matter the way I draw this, I'm going to put 2 resistors on top. Then the 5 ohm resistor, then the 4 ohm resistor, and then finally through the 2 ohm resistor again here, and back to the negative terminal. Again, it doesn't matter if I had put, say for example, the 7 ohm one up here, and then 5, and then 4, then 2. Or maybe 7, 5, 4, and then put the 2 one up here. As long as they're really in the same order that we started with. 7, 5, 4, 2. 7, 5, 4, 2. Leaving the positive terminal. Notice I drew it going this way, whereas here it would go this way. But it really doesn't make a difference in this sense, as long as they're in the right order. Now, at the next part, I'm going to say I want to find the equivalent resistance of the circuit. And if I remember my law from a moment ago, this is what the law said. Okay, the sum of all the resistances. Therefore, I could simply say that I could replace this with one resistor that is the sum of all of them. So 7 plus 5 plus 4 plus 2 gives me a net resistance of simply 18 ohms. So this is what I can write in my diagram. Now, the voltage on the battery was 9 volts. So let me add that to my diagram in each spot. Now, if I know what the voltage is, and I know what the equivalent resistance is, I can determine the current in the overall circuit. So let's use Ohm's law, saying V equals IR, and therefore I equals V over R. V over R would be 9 volts over 18 ohms, which would be 0.5, right? 9 over 18 is a half. And my units are amps. So the current in the circuit is 5 amps. That's the current through all of the resistors, because remember, in series, the current in the circuit is equal to the current across each resistor. The last part we want to do here is to find the voltage drop across each resistor. Now, to do that, we have to think about the fact that each resistor also follows Ohm's law. So for the first resistor, we have this, but remember that the current, we don't really need this subscript of a 1 here. Why don't we need that subscript? Because the current is the same in series across each resistor. So if I want to find the voltage drop, I just simply take 0.5 amps times the 7 ohms in the first resistor, and I get 3.5 volts. For the second voltage, I'm going to do the same thing. Take the current of 0.5 times R2, so 0.5 amps times 5 ohms, giving me 2.5 volts. And let's take a look at the third and fourth resistors. The third and the fourth resistors follow the same law, IR3 and IR4. Therefore, we have 0.5 amps. Here we have 0.5 amps. This is times 4 ohms. And this is times the last rating of 2 ohms. So that gives me 2 volts, and this gives me 1 volt. So these are the voltages across each resistor. Now, the last thing we'll notice is this. If we sum those together, this proves our law from earlier. Our law from earlier said the voltage in series across the terminals is equal to the sum of the voltages across each resistor. So since we have 4 resistors rather, if we add these 4 numbers together, we end up getting a value of 9 volts, which was the voltage across the battery. So what we want to look at next is the fact that a series circuit requires all elements to conduct. And what you'll see here is this. If one bulb goes out, they're all going to go out. And you remember this from Christmas trees. When one of your light bulbs went out, the whole strand of bulbs would go out because they were connected in series. Now, today a lot of them are connected in series and parallel. So you'll see one go out and only a little section will go out. We'll talk about how that works when we get to parallel circuits. But what happens is the charge carriers want to flow, but when there's this opening, there's this gap, the EM field is no longer established, so it's not going to push the charge carriers through. So this creates an open circuit. Now, you might say, well, why would you ever want it in series then? It doesn't make sense if this could create an open circuit. But the reason is that sometimes it's useful if you want to regulate the current. And we'll see that a little bit later how this works, because if you notice a moment ago in the last example, remember the number for the current in the system was only half an amp. And we're going to see in a little bit, we're going to use the exact same example in parallel, and we're going to see that our current is not going to be a half an amp anymore. The current in the circuit is going to be much greater than a half of an amp. So if you need a low current, you want to regulate your current, you would probably choose partially a series circuit. Okay, but again, a lot of circuits now are made of series and parallel mixed together. Now for a parallel circuit, we'll look at the same 3 things. We'll look at current, voltage, and resistance again, but now it's in parallel. So think about, again, like water flowing through a pipe, but now think about this. Water's coming through this pipe, and now imagine the pipe branches off. into two branches. What would happen to the current, right? There's a certain amount of current flowing through here, and if these pipe dimensions were the same, the current would dramatically slow down in each pipe. So again here, we're going to notice now for the current though, the sum of the currents across each resistor is equal to the total current leaving the battery. So we could say that I in the total battery equals the sum of the currents. Whereas last time, we said that the currents were equivalent across each resistor. Now it's not. Now we could say that if, there's a total current of, say, 10 amps, each of these resistors has part of that 10 amps. They don't each feel 10 amps of current flowing through them. The second law is the voltage law, which is a little bit confusing, but we'll try to explain it here by considering the fact that the positive terminal in a parallel circuit, and I'll draw it at the top, but the positive terminal in a parallel circuit, right, so here's a parallel circuit, and this positive terminal here is connected to each lead, right? It's connected there and it's connected there. Now, what that means is that since it's connected to each bulb and not just the first bulb, that the voltage is going to be equivalent across each of these resistors. So we're seeing this now. So what we can say is that, if you want to just remember this, the current and the voltage laws are the opposite in parallel. Earlier these were all equal signs and these were all plus signs, whereas now these are all plus signs and these are all equal signs. Now to derive the resistance law, we're going to do the same thing as we did in series, except now we're going to notice that since obviously V equals IR, we have it this way, we can solve for I in that equation and say that I equals V over R. And now instead of writing V equals V1 plus V2 like we did in series, we're going to write out our current law. I equals I1 plus I2, etc. So imagine there's only two resistors, this is what we have. Well, that definition of current is voltage over resistance. So let's replace all of these with voltage over resistance, yielding V over the equivalent resistance equals V1 over R1 plus V2 over R2. But we recall from a moment ago that the voltage drop across all the resistors is the same. So these V's are all identical. So instead of V1 and V2 and V3, let's write it out again like we did earlier, but with just V in each of these. Again, earlier it was just I in each of them. Now it's just V in each of them. Well, again, what we can do is we can factor out a V on both sides. So this becomes V times 1 over Req. And on the right-hand side, this becomes V times 1 over R1 plus 1 over R2. These V's cancel on both sides, yielding what's called a reciprocal sum law. What we can say is this: the reciprocal of the equivalent resistance equals the sum of the reciprocals of each resistor. So as a law, it would look like this: 1 over Req equals 1 over R1 plus 1 over R2 plus dot 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 1 over Rn. So the law is pretty much the same idea. It's still a sum, but instead of being a sum of resistances, it's now the reciprocal sum of resistances. So example 2 is pretty much the same as example 1, but now we're looking at a parallel circuit. And we can see that it's parallel because the positive lead here, okay, or either one's positive, doesn't matter here, connects to this terminal, and then it connects to here, and it connects to here, and here. So we have this parallel circuit now. So what it looks like is the following. And each of these resistors here has its own branch, and it's in parallel. So this is 9 volts, this is 7 ohms, this is 5 ohm resistor, this is a 4 ohm resistor, and this is a 2 ohm resistor. So now we have to look at our resistance law. Remember that it's 1 over Req equals 1 over R1 plus 1 over R2 plus dot 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 1 over Rn. And this is going to be a bit confusing at first because we have to do a little bit more math than last time. We end up getting, let's see, 1 over 7 plus 1 over 5 plus 1 over 4 plus 1 over 2. Now in this case, you can find a common denominator, come up with a fractional sum, and then take the inverse. Or it might be a little bit more useful just to add together those fractions and round to the nearest decimal. And the reason I say that is really just because it's easier to do it on your calculator than finding a common denominator. So if you add those fractions together, you end up getting approximately 1.09. So 1 over Req equals around 1.09. So how do you find Req? You take the inverse of both sides. Right? If you want to find 1 over something, you want to find Req, invert that sign, or the reciprocal. So you really want to raise this number to the negative 1 power. So RQ is really 1.09 to the negative 1, or the inverse, which is really just 0.917 ohms. And this is really interesting to notice. Earlier, when we found the equivalent resistance in series, it was a value of, I think, 28 ohms, which is a much larger value than any of the values, or 18 ohms rather, 18 ohms, than we started with for each of the resistors. But here, the equivalent resistance is suddenly much, much less. And notice that this equivalent resistance here is less than all of these original resistors. The original resistors were 2, 4, 5, and 7. This number is far less than any of them. So what you can say is that in series, the sum of the resistances, or the equivalent resistance, is always going to be greater than any individual resistor. Whereas in parallel, the equivalent resistance is always going to be less than any of the original resistors that we had. Now let's draw the new circuit, what it would look like. So this new circuit would still have a positive and negative lead, but now we just have one resistor, and its resistance would be 0.917 ohms. This is still 9 volts. Now the next part says we want to find the current in the circuit, so we'll still use Ohm's law again, V equals IR, and solve for I equals V over R. But now look at this, the voltage over this really small resistance. Earlier we took a voltage of 9 volts and divided it by 18 ohms to give us a small current of half a current, or half an amp. But now we're taking 9 volts and dividing it by 0.917 ohms, which means that this answer is going to be much greater, because clearly we're dividing by a decimal, so the number is going to get larger here. So you end up with a current in this problem of 9.8 amps. Huge difference than when we're in series. So in series, if we have resistors connected, the current is going to be much lower than the current felt when it is in parallel arrangement. The current again in series was 0.5 amps. The current here is 9.8 amps, almost 20 times the value of the current that it was when it was connected in series. And that's why earlier we said that if you want to control the current or limit the current, you would set up your elements in series to reduce the current. But if the current doesn't matter in this case, or the current can be a larger current, you could have them set up in a parallel arrangement. Now the last part we want to figure out is to determine the current in the current through each resistor. Current through each resistor. And the reason we're going to do that is because we remember our current law said that the sum of the currents equals the total current. So let's find the current across each resistor now. And to do that, we're going to say that current in the first resistor is equal to the voltage across the first resistor over the resistance itself. Now, remember that the voltage is the same across all resistors, so this is always going to be 9 volts, but the first resistor is 7 ohms. So the current in the first, or across the first resistor, will be 9 over 7, which reduces to approximately again, 1.29 amps. In the second resistor, we can find its current by taking V2 over R2. But remember that the voltage across the second resistor is still 9 volts. These are the same, notice, because our voltage law in parallel says that V equals V1 equals V2, etc. But the resistance is different in the second resistor, and that's a resistance of 5 ohms, giving us a current of 1.8 amps. And then we do the same thing for the third and the fourth resistor. Again, 9 volts over its resistance, which is R3, and that's a resistance of 4 ohms. And that's going to give me a value of 2.25 amps. And then finally, the fourth resistor, 9 volts over 2 ohms, which gives me 4.5 amps. Now, if I take these four values of current, what I'm going to notice here is that when I add them together, they do indeed sum up to the original current in the problem. And the original current that we solved for was 9.8 amps from earlier. Remember that number. And our current law, remember, tells us that the sum of all the currents is equal to the original current, or the current through the whole circuit. And these four numbers, 1.29 plus 1.8 plus 2.25 plus 4.5, is indeed approximately 9.8 amps. The reason it's approximate is because we rounded earlier when we did the equivalent resistance, so there's going to be some rounding error in the problem. Now let's take a look at resistors in parallel, and they do not require all elements to conduct. So if one goes out, the flow of electrons continues through the remaining paths. And let's illustrate this. Imagine, if you will, that this did not exist, this entire path. It went out. Right? That bulb blew and there was no longer a path there. Well, it doesn't matter, because the voltage is still going to, or the charge carriers, the voltage will push the charge carriers through all the rest of these continuing parts. So even if all of them went out, except for the last one, you still have a completed circuit. This would still pass through this entire thing. So in parallel, if one bulb goes out or if one element stops working, the others continue to conduct that flow. So finally, in summary, let's take a look here. In series and parallel, the schematic in series looks like this, where the two elements are one after the other, thus the word series, they're in series. And when they're in parallel, we see that it branches off, and we can see these lines are parallel to one another, hence the word parallel. The current in series is the same across each resistor, whereas in parallel it's the sum. And then it's vice versa for the potential difference, or the voltage. The voltage in series is the sum of all the voltages, whereas the voltage in parallel are equivalent. So equals and plus, whereas this is plus and this is equals. And then finally, the equivalent resistance in series is the sum of the resistors, whereas in parallel it's the reciprocal sum of the resistors.